Hello, everybody. Welcome back to Scientific Terminology. Today, we're going to be talking about gravity, and it is a force that brings us all together. The lovely message of gravity. So, we're going to talk a little bit about what gravity is and how we came about understanding how it works. So, first of all, what is gravity? Like I said, it's an attractive force that increases based on the amount of mass present in objects. All mass creates the force of attraction known as gravity. However, only really large masses have noticeable pulls, right? So even you and I, right, can generate gravity, but that force of gravity is so small we don't feel it. Gravity is a universal law of nature and one of the major pillars of modern physics. Okay, so it's an important part of our understanding of the universe. The first guy who really kind of helped us understand exactly how gravity works was Isaac Newton. And that's because he was able to investigate and apply mathematics to gravity. Using his mathematical skills, he was able to use Kepler's laws of planetary motion to determine the strength of gravity and write an equation that could describe it. Newton was originally accused of trying to add the occult into science, since he described gravity as an invisible force that acts over long distance, which sounds kind of like an occult thing, right? But in reality, right, that's what it is. So Newton's universal law of gravitation still stands, right? It still works. And the law states, in today's language, that every point mass, so every amount of mass, attracts every other mass by a force acting along the line intersecting those 2 points. So basically, if you take two things, let's say like Earth and the Moon, and you drew a line between them, there's a force that goes along that line because these things have mass. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. So that means that how far away they are, as well as how much mass there is, matters. Here's the equation right here that he wrote. And G is a constant that makes the math work. It's one of the natural constants. Sometimes in scientific equations, we just have to have these numbers in here. Otherwise, it doesn't work out. And this is one of those numbers. M1 and M2, like I said, are the masses of the objects, right? Mass of object 1, mass of object 2. And then R is the radius between them. So the distance of that line in between the two objects is R. Now, Albert Einstein kind of made an upgrade to Newton's theory of gravity by combining it with his theory of relativity. In order to generalize special relativity, Einstein introduced his theory of general relativity that explains kind of how gravity works. Einstein's theory of relativity is widely accepted, however, has not yet been reconciled with quantum theory. So his theory holds with all the available data, but one of science's biggest issues is that we can't seem to reconcile the stuff that happens when things are really small with the things that happen when things are really big. So that's something that scientists are working on right now, trying to figure out how those two things can be combined into one general theory. So our modern understanding of gravity is that Newton's explanation of gravity has been added onto, and relativity is what's going to make it more complete. Relativity states that the relationship described by Newton is actually due to the curvature of space-time. So before, Newton was just like, look, big things attract each other, and it's based on how far apart they are and their mass. And relativity says, yes, that is true, but it's also because big things are curving space-time, and that is causing that attraction. So basically, things that are close to bigger things fall into a free fall around them, and that's the attractive force. Objects with more mass bend space-time more, and that causes a larger force of attraction, which is why having more mass gives you more gravity. Understanding gravity in all of its conditions and its relation to relativity is a major part of modern physics. So here's what I mean, right? Here's Earth, and it's got a lot of mass, so it bends space-time a lot. And so things that orbit around the Earth, like the moon or satellites, are really just in free fall, around the planet. So basically what's happening is, if you imagine jumping out of an airplane, right, you're in free fall, you're falling down towards Earth. But if you get far enough out and you're going fast enough, like a satellite or the moon, you're going to free fall continuously circling around in this thing, kind of like a penny in those wheel things. You put the penny in it, it circles around until it finally goes in the hole. Same idea, but it's not going to go all the way in the hole because it's going fast enough, right? There's no friction slowing down the moon. So general relativity, right, took this classical explanation and modernized it to answer these new questions that were brought up in modern physics. Einstein's theory added another variable, time, which complicated the math. Right now you have to use calculus to do this sort of thing. And Einstein's general relativity has stood the test of time and has been consistently held up by experiments. So we know through many experiments that what Einstein was talking about passes based on physical phenomena. So right, our observations match what he was saying. Gravity ultimately is incredibly important. It's one of the major pillars of modern physics because it describes the motion of all the big things in the universe, right? It describes why the big stuff happens. Gravity and general relativity have not really been shown to hold up at the quantum level, though. So when things get really small, gravity and general relativity don't work the same way they do when things are really big. This, right, is the big issue facing physicists. How do we reconcile the fact that when things are really small, stuff acts a certain way, and stuff is really big, it acts a different way? So this is going to, if we figure this out, this would solve one of science's big remaining mysteries, right? There's some big major questions in each branch of science. One of physics is this one, right? How do we reconcile these two things? Thanks so much for watching Scientific Terminology again, and I hope you enjoyed and learned something from the video. If there's something that you want to learn about that hasn't been covered on the channel yet, go ahead and comment on the video. Tell me what you want to learn, and I will make a video about it so you can learn about that thing. And other than that, thanks for watching, and we'll see you next time we talk about something in science. Thanks again, and we'll see you next time. Bye.